Okay, more physics. So now I put a couple of more exercises there because we use where we actually would use this topic of the week, the right angled triangle. Hopefully my English will do this presentation as well. And so a couple of things, maybe you will also calculate that kind of calculations in the physics later. But we will try a couple of like sort of simple things. Hopefully they feel understandable or sort of okay for you as well. But that's just, it's nice to have also here in the math something that you calculate something where you could actually then use it in the like sort of reality. For sure, in physics, you heard about the Newton's second law and things like this. Forces, something like that. You've been monitoring with Jaakko with some gadgets. I'm putting the data in the Excel or something like this. Yes? Good. So I created this kind of a presentation quite quickly with AI. Let's see if this works. And then we do a couple of examples. Like exercises. So then we can do them together. Okay. I think, yes. So Newton's second law is that net force equals mass times acceleration. And when did the Newton think about this? Everybody maybe has heard about the circumstance or seen the picture that there was maybe he actually realized that there's gravity or something, yeah? When there was the apple hit his head or something like this. Yes? But anyhow, so the acceleration for the apple would be, of course, the gravity of Earth, yes? The Earth pulling the apple towards itself with a constant acceleration. That's the gravity. And it will come here later. But anyhow, net force equals, he formed this kind of, he formed the concept of force. Force equals mass times acceleration, yes? And here is just some force and some mass. Well, it would have been the mass of the apple, and then this A would have been what would have it been? Which number? Do you remember already from the physics? 9.8, yes. Or 9.81, yes. So, but then of course there might be more forces affecting something than just one. So in the apple, with the apple, there was just the gravity pulling it, yeah. But there might be something else as well. So all the forces that are affecting towards a certain direction have to be calculated together. And then that totally comes to the mass times acceleration. Yes. So force and acceleration are vector quantities. Net force sum of all forces acting on an object on that certain direction. You can't, all the forces that act to whatever directions, you can't calculate them together like that. You have then to put them into the components. Did you do that in the physics? But this is something that you will do later, and this is something we should do now a little bit. And you did this with the help of the right angle triangle, haha, which was the topic of the week. Okay, so here is a very simple example. Just if car is pushed with net force of you would know this, how many newtons is pushing the car. You could, for example, calculate the acceleration, yes? So you know the mass, you know the force, and you can calculate the acceleration. Usually it's not this simple, yeah? This is not really maybe a real world example. Biggest forces acting on an object include weight. Yeah, this was the apple. So then the normal force, if something is stationary here on the table, there's the you say there's the normal force, it's not going anywhere. It's the supporting force of the table. And then there's the friction. So if something's moving on for example, a car or whatever, the friction, you'll be maybe monitoring this with Jakob, I don't know. So then there's the engine force or applied force. You know, you're burning some fuel and you're getting some force from the engine. You're actually going forward, even if there's some forces acting. For example, the friction that would try to keep you still. Yes. Air resistance, if considered. I don't know if in physics calculations you go that far, but we don't consider it here. Okay, gravity, force pulling objects toward the center of the earth. The formula. So I mark it now with the big G here. So there's, as you know in physics, you can use many kinds of letters to describe many kinds of phenomena, and then you find them into the technical formulas, basically. It uses certain ones. I usually use for the gravity, I use the big G, because it sort of makes it look different from the other forces, yeah? But you can also use some other letter if you're used to that. But you know that it's the mass times the gravity. Acceleration, and oops, this unit is a bit on the wrong place, but anyhow, it's 9.81 and meters divided by second squared acts vertically downward. This is not really vertically downward, this picture, but it acts vertically downward. Yeah? Good. So a car that has a mass of 1,000 kilograms has the gravity or weight. In English, you say mass and weight. And in Finnish, we sort of use the same word for both, and then it mixes up the students, maybe even the teachers. Or maybe in English, you also use the weight to mean mass. Yes, sometimes. Yes. But okay, the car's weight is then this number, the small g multiplied with the mass, which here would be 1,000 kilograms. You already maybe know all these things. So then there's the normal force that I told. It's the support force exerted by a surface, and it's marked as a perpendicular arrow to the surface. Yes. So the gravity goes downward and the normal force upward. It balances the perpendicular component of gravity. Okay, perpendicular component of gravity. Now it's easy here when we are on a horizontal surface, yes? So the gravity goes downwards. But then if we are on an inclined plane, it still goes, of course, towards the center of the earth. But the other forces then, for example, the supporting force comes straight to the inclined plane, yes? This normal force. Does it make any sense what I'm talking?
Yeah.
Yeah, it makes some sense. Good. Okay. Anyhow, the normal force prevents objects from falling through the surface. Okay. That would be a bit weird if that would happen. On a horizontal surface with no vertical acceleration, the normal force is the same as the g, as you can see from the picture here. So you know, something is here stationary, then if you add them together, it has to be, you know, the acceleration is also 0. Yes? So other one is upwards, other one downwards. So the n minus g would be 0 and n would be g. Did you do something like this in physics already?
I think I remember this from school, but
Okay, cool. Somebody even remembers you had a good school. I don't remember anything from physics from school. Nothing. Okay, so here also for this car that weighs 1,000 kilograms, the normal force would be the same as the this gravity force that we just calculated. Yes, as we realized here, and we will still look at it on the paper. When on a slope, gravity splits into two components. So there's one that's perpendicular to the slope, would be something like this, maybe. Maybe this is an electric car. Yeah, cool. Yeah, this is the what the AI gave me, the pictures. It looks cool. For this car on an incline, the normal force, then we would have to multiply with cosine of this 10 degree incline. Maybe like this. And then we could also calculate the parallel force. Okay, now it gets a bit more complicated, and here we need the right angle triangle. Key points out that gravity acts vertically downward, normal force is perpendicular to the surface. So okay, on an incline plane, they are now pointing to different directions. Yes, so that's why we needed to put this gravity into two components. And then you can calculate the normal force. But then there is also the friction that we talked about, so it opposes the motion. Otherwise, we wouldn't be also maybe moving if there wouldn't be any friction, yeah? So it's very crucial force. And here is marked this kind of some kind of box moving horizontally with some kind of acceleration. So here is the mg and the normal force, the g and the n. Then the friction. This is the friction. You usually mark it here, yeah? Because it sort of tries to prevent you from moving forward. Okay, so this is still car on incline plane. We looked at this. There's an example calculation, but okay, whatever. That's it. We don't need to look at that any further. Now we can just try to calculate those exercises. I hope I already managed to put them there. So they would be the last ones here. The 8 and the 9. Maybe we start with the 8. So here, surprisingly, the mass of the car is 1,000 kilograms. And then there is the coefficient of friction as well. Hey, one thing, did I remember to tell you? Sorry, I'm going so... Now I lost that. Why I can't get it back? Oh, maybe it's behind that. No, yes, I'm back there. Where did I need the friction? This is not a great presentation. Sorry about that. So the friction is always, do you remember, or did you go through with this with Jaakko yet? the friction force is always the friction factor multiplied with the normal force. And this is how it is always. Is this a familiar equation to you at all? To who this is a familiar equation? Who has seen this equation before? Okay, so maybe you saw it in some different school, but not here. Okay, so this is how this all is connected, interconnected. So you need to calculate the normal force. And then when you're on horizontal plane, it's really easy because it's the same as the G, yes. So you just multiply the mass with the small g, 9.81, yes. But then when you're on an inclined plane, you can't do that anymore because the G is pointing like this and the normal force is pointing like this if the incline would be like upwards, like now it is there in the calculus. So the normal force is here, but the G is towards the center of the earth, yes. So this is the really important equation that you need. Okay. Let's go back to the calculations. Oops. But these are like some kind of like if you went to any school and did any physics, these are really, this is something that you will always end up doing, this kind of calculations. So I don't wonder that maybe some of you find this familiar already. But it's also a good example of using the right angle triangle in a sort of real world. Is this the real world? So we have a bar with the mass. And this is also good because now we have some letters that we have also values to. So you have to put the values into the equations. This is, of course, what the engineers always do. What you also do in physics, yes? And then there was the coefficient of friction. You can mark it either as U or little f or how you are used to mark it. And then there is the car. And then at first there is the calculation of car moving on a constant speed on a flat surface. So the first thing is, of course, that you draw the forces. It's moving, so it needs some kind of an engine force. That's my engine force there. And then, of course, the friction force. So we can't really, as the first example, where, well, okay, if I know the net force, but usually you always have it like this. Here would be the friction force. I can mark it, for example, F and little f there, so it would be the friction force. So this is the force engine, for example, like this, and this then is the friction. Then you also had the two other forces here. So there was the G, I mark it with G, and then there was the N. And now we would need the Newton's second law. Newton's second, which was all the forces calculated together towards certain direction are mass times acceleration. And then we also knew that the G here, for example, put it like this. G is the mass times small g that the Newton figured out. And then the other friend here, the friction, that's always the, I'll put it, for example, on this side, that is always the friction factor times the N. So this friend here. And with this information now, you should be able to calculate the the force for the engine. And here on the 8, it says that the car moves at constant speed. Do you know what that means? Yeah, so how about the acceleration here? If it moves at constant speed?
0.
Yes.
Yeah.
So then you get to write one more thing there, yes? Acceleration 0. Okay, so now, what do we do now? What do we need here, of course, are the axes, yes. So there's the y-axis and the x-axis. This is y and this is x. X is always on the direction of the movement. And y is the perpendicular. Perpendicular, yes.
Yeah.
to the direction of the movement. And also the engine force, basically, because that is always in this kind of calculation thought to be in the direction of the movement, yes? Can we now calculate all these, because you know what this means, yeah?
Oh, some.
All sum. Okay, can we now calculate all the forces together? Which forces do you see in the picture for? Yes, you see the friction,
Yeah.
the engine, the G and the N. Can we calculate those 4 forces now together?
Oh, okay. Yeah, but then I don't. 1,000 times 0. What was 0? No.
Yeah. There's many things in this that are a bit intriguing. Is that a correct word? Now I'm learning. Sometimes my English is amazing. Sometimes it's really bad. Yeah.
Very good.
It's nice to have these sensations that sometimes you are able to say what you mean. Yeah. Okay. So acceleration is 0. So we got to 1 point. Yes. Okay, I'll do something here. I would think like this. First, I would think like this, that some of my forces here, I see the forces in the picture and I start putting them there. There was the friction, there was the engine, there was the G, and there was the N. And then this is M times this thingy, okay, 0. Is this correct? What is the problem here? Can anybody see a problem?
Gravity would be like that.
So what was it called? What was it called? Because it's so difficult to vector force. Vector force. What does it mean to have a vector force?
That one, it's got speed and it's got 2. I can remember it.
It's got the some kind of a number, like what?
Yeah.
Some kind of
Direction.
yeah, it's got like a number, like a how do you say? It's either big or small. Some kind of a, for example, 1,000 kilos is that a okay, but this is not a vector. Now my English went away again. Anyhow, it has got some kind of like how do you say, what is this, like a mass, but then well, a number. It's big or small, it's whatever. In the example, for example, force was 4,000 newtons or something. It might be big or small. Okay, but what else does a vector
Direction.
Okay, so what's the problem now here?
No direction.
Yeah. Okay, so can you calculate something like this together that has different directions? Can you calculate those just like that? No. Okay, this went completely wrong. We did something. So we can only sum together the vectors. Okay, now I'm almost teaching you vectors, which should have maybe been even part of this course. So the ones, those arrows, those forces that are pointing on the same direction, you know, so it can be pointing like backwards or what is the other?
Forwards.
Forwards, yes, backwards or forwards. How do you, let's do like this then. We take everything here on the x direction, yes. So we sum them all up together. So there's the F. How about this? If it's pointing to the other right direction, how do we mark it? Of course, you also need the directions. Maybe we put the minus here, yes?
Yeah.
And then this was the mass times acceleration, but we already realized that was 0.
Yeah.
And here we would get the result that the engine force that I'm needing now when I'm not accelerating, that would be the just to compete the friction. Can I say like this?
Yeah.
Okay. And then we can sum together those forces that are pointing to this direction as well. So that's in the y direction, yes?
Yeah.
So there would be n upwards. I like to put it this way because I like to write the minus after the plus sign, yes? So n would be upwards to the plus direction and g downwards.
Yeah.
You just have to pick the directions and keep it up. You know, of course, you can pick them the other way as well.
Yeah.
And then you get different signs. Okay. And how about acceleration here? Well, it's the car doesn't even, it's just moves horizontally. So there, of course, there's nothing, you know, it doesn't, we think that it's just moving like this. This is a simplification. So here we get this result, n is g, or, you know, that we had already on in those. Here, as you see as well, you have the supporting force so that they have to be equal.
Yeah.
But it actually comes from this, yes? Okay. Now we are almost done. Yes, because what we actually needed here was this. So we have it here. We have solved it. How to solve this until the end?
$1,000 now. Is that it? No. Well, yeah.
So we try to do this like properly now with all the letters. You know something now. What is this? The friction force is always this. Friction factor times the normal force.
So then that would also be 0.
Okay, so let's take a look at this now. I have taken the F from here. I have figured out that my F is actually the friction factor times the normal force.
Yeah.
Because it has to be the same as the opposing force, which is the friction. Yes. The engine force is the same.
Yeah.
Yes. So now what I figured out from the other equation here is that the normal force is the mg. Yes.
Yeah.
Now I can put it there. Yes.
Yeah.
So here I figured out that this is this.
Yeah.
And I can put it there. Does this make any sense?
For me, it does.
Okay, so who thinks this makes sense? Yeah. Did you do something similar in physics? Yes. But maybe not yet in the physics course here. No. You did something maybe similar, but you didn't realize that you did it. Because you measured it and you put it in the,
Yeah.
and maybe later on you'll figure out, you will start to think like, you will go through what you actually did. I don't know. Okay, so now I know that my engine force here is this. And now I can calculate it. Here. This is of course what I knew from before.
Yeah.
So the G, what is it called in English? The gravity acceleration, or
Yeah.
yeah, it's the 9.81. And that affects to us all who are here on the Earth and all the objects, yes? So then just that there. So it's actually what we calculate here, this is 1,000 times this, and then times, so then you have the one-tenth of this. And then you get you get this, what is there already in the brackets, or you actually get this. That you can round 208 meters. But now we should do that on the inclined plane.
So
Do you think that's doable?
that'd be
But ask now if there's something you were thinking, for example, why isn't it all zero or something?
Yeah.
No, it's just that this net force here. So the acceleration, this also has the direction, yes?
Yeah.
So it can be either there is no acceleration on this direction, but then there's also no acceleration in this direction, you know, like where it moves. The horizontal direction or x direction, like we mark it here.
also.
So as it's taught with this law that now if you have an object that's moving on a constant velocity, then all the net forces affecting to that direction that's moving at constant velocity are also zero. So you need only some force here to actually, you know, kill the other force that's trying to resist the movement.
Yeah. So that 980.
So you need, of course, some kind of force, but this is only to kill the friction.
Yeah. So that would be in there.
but not for the acceleration. If you have acceleration here, then you just have one more term. You have the mass times the acceleration. So then you need also petrol for that. Yes. When you're accelerating, you're using more.
Yeah. Yeah.
Force. Yes. Okay. Yeah. Do you think this is interesting?
Yeah, I love them.
Is it a bit like is there already too many letters and too many arrows and too many things? Does it look a bit like unclear?
It reminds me of like algebra a little bit, but
Okay,
yeah.
let's go on an inclined plane then. Okay, and we are going uphill. So it's 5 degrees. Well, I just draw it, it doesn't matter. I just mark there, that's 5 degrees. It can be anything, and it's always the same procedure, of course. Yes. This angle can be, any. Can be big or small. Well, usually it can't be really big. I don't know if you're driving up a hill, like a really steep hill, just like that. You need quite a lot of maybe that. So I have the car here. And then I would need to calculate this force again. And again, here I have the force. Then I have the friction. The friction. Then I have the gravity. And then I have the supporting force from the plane. Hill. Here. So this was gravity always towards the center of Earth, and then this supporting force is perpendicular to the plane. Or how do you call it?
Yeah.
Plane. So now I know something. I know that first of all, I know that I can't calculate all the forces together. And now they are even before here. I had an easy calculation because the forces are pointing on the horizontal and vertical direction. So I had two directions. But here it looks like now I have 3 different directions. Yes?
Yeah.
So what I need to do is to decide where is my y and x directions. Yes? But the x direction I always have towards the direction of the motion. So what do I need to do? I have now these forces are nice if I choose these axes like this, because they are still on the x direction. I can start calculating them together. So again, I know from the Newton's second law the same thing. And then I would start calculating all the forces in the x direction. There is my F, that would be the minus sign. Then I have this force that I'm trying to calculate now, how much petrol I need or something. And then I know also that this is the mass times acceleration. Well, I'm not accelerating, I'm just trying to keep moving, but obviously maybe I need a little bit more force here. because I'm going upwards. But then I have something here still that's causing me a little bit of problem. If I start calculating the forces also now to the y direction, I have there the n. Yes, that's my nice force there. Okay, this is the same direction. This is perpendicular to the plane. But how about this g? What do I need to do with it?
Why?
Yeah, the components,
Yeah.
yes. So this is like, it can be called vectors or components.
Yeah.
So you can, but you can draw anything in on a, like this kind of a y-x, where you have with the coordinate, some kind of an arrow.
Yeah.
And then you can, tell its greatness by the vectors that are pointing to y and x direction. Yes.
Yeah.
So there are the I and y.
Yeah.
I and I. Okay. So for sure you've calculated vectors sometimes. Maybe we could be calculating them here as well, but now we are just talking about the components of the force, and that's actually exactly the same thing. Yes. So we can express the greatness of our great G force here by its components to the x direction. So this would be the x component, and here the y component. Yes.
Yeah.
And these both have to be pointing so that we come from here where this arrow starts.
Yeah.
To the end of it. With these two components that are perpendicular towards each other.
Yeah.
Yes.
So then you have 9.8 as the apologies.
So now, if I'm calculating all the forces here on the x direction, for example, I got one more force here, yes. So the x direction, x. There is the F that I'm willing to calculate, like I need to know, but then I also have this there. It's also to that direction now.
Yes.
But now this G turned into a nice force as well, and I can put it to the X and Y, my X and Y direction calculations. So it fits there, yes. And then here I got this. This is exactly what the slides were saying by the AI. So here we can now calculate the normal force. It's not the G anymore, but it's the Y component of the G force. Yes. So let's put those things there. There's which direction is this now? What kind of sign has it?
X. So
But if I put it there, what kind of sign do I add?
in the no,
Is it
the little arrow
positive or negative?
or negative.
Negative, yes. Negative there. And then there is the N upwards, and of course this G Y downwards. Yes. Wow. What do I need now? The components, maybe, yes. Now here I need the right angle triangle. Finally, we are there. How can I do that? What angle do I have here up? How big is that angle?
Is it written down somewhere?
How do I know it?
I don't know. What? Because
But what is it? You know what it is. Maybe somebody of you know, or maybe even many of you know how big it is. How big is it? This angle here, how big is it?
5 degrees.
5 degrees. Yes, just like here, 5. Can you tell me why it's 5 degrees?
I don't know.
I don't remember the law behind it, but
Yeah. You don't just remember, but you remember calculating this kind of calculations where it's always the same angle as the inclined plane. Yes,
yeah.
exactly. Does anybody remember or know why it is actually 5?
Equivalent triangle.
Equivalent triangle. Yeah, equivalent triangle. Okay. And then you can also see it from here. So if you have a straight angle here, we can call this a straight angle. Like actually like this kind of a thing is a straight angle. Yes. Okay. So I have here a right angle triangle. Here, right angle triangle. And then also here I have a right angle triangle. Yes. Like that. So now I know that here this is 5. So this is, how much is the right angle?
90.
90, yeah. So how much would this be?
108.
Yeah, so it's
Yeah.
it's 100 and it's totally 180. So
Yeah.
it's 180 minus 95. Yes?
Yeah.
So then it would be 75. No,
65.
180 minus 95.
85.
85, yes. $85 here. So I know that this angle as well. There. Yes. And then how about this angle here of this? So now I'm talking about this triangle here. I'll mark it. This triangle. This triangle here. Okay. That we are talking about. But there's also an angle here after this angle. How big is this angle here?
90.
So yes, 90. So this is, of course, this was the y component, and it has to be perpendicular to this because this is the x, you know. So that has to be 90 here. This starts to get a bit like, okay, 90 here. 90 there. Bit like messy looking. Okay, so if I know that this is 85 and this is 90, how much must this be? 5, yeah. So that's how I know that it's 5.
Okay.
Yes.
Yeah.
Okay, cool. Now I know that for sure. So then I was doing some calculation here. What was I actually calculating? This?
Yeah.
It starts to look really messy now, doesn't it? So maybe what I should do is to use, I've been now in the triangles very nicely, you know, I've been figuring out some laws, and now I can also maybe figure out the gx and gy components here with the help of this angle. So if I start writing, for example, the sin for this angle, sin 5, what would it be in this pink triangle?
So the 9.8. No,
So what is
So
the
it'd be
sin? What
A.
is the sin always?
x over 9.8.
It's the opposite,
Yeah, so you,
gx,
yeah,
divided by
g.
g. From where I can figure out the gx.
Just grab it to 9.8. Is it not?
Yes.
Oh, yeah, okay then.
First, I solve this. So I will solve now the gx. What is the gx? I just multiplied the g away, yes?
Yeah.
So I have multiplied the g from here. So I get g times then 5. Yes?
Yeah, yeah.
Okay. And this is maybe what the AI already gave us as well. This was the one that was parallel, the parallel component. And then in the same way, I do the gy. Oh, well, now I'll just write it from the beginning. So cosine for the 5. What is it?
0.99.
It's again the gy
Oh,
now,
that's it.
which is the this side of this triangle that is not opposite, but what is adjacent.
Actually, yeah, it's,
And from there, I can figure out what is my gy. So this is where actually my I had to use this right angle triangle. In this kind of calculations, you always end up using it. Now I can calculate the f with all these equations there and all the dependencies. As long as I also remember the formula that I always have to know that the friction force is the friction factor times the normal force. This is also something that I always need in this kind of calculation. So now you can continue the way you want. For example, you know that there was no motion in this direction, yes?
yeah,
So this is 0, and you know also that now that the n is the gy, yes?
Yeah.
From there.
Yeah.
And gy you already calculated. So it's the g cos 5 degrees. Yeah, of course, you need to also know that the G is, the G, what I marked with G is the mg. Mass times the gravity acceleration, or what is it called in English?
Yeah.
This one you have to modify a bit as well, yes?
Yeah.
So to solve the F from there. So what you got, you had no acceleration, so you had there. Oops, minus friction. Then you had the engine, and then you had also this component of the gravity trying to resist your going up the hill,
Yeah.
of course. That makes sense, yeah? Minus gx. And this was 0 because the acceleration was 0. So the engine force, you need to compute the friction plus the gravity. Does that make sense? But you don't need to accelerate anymore. If you would be accelerating, you need to even more force. Yes?
Yeah.
Okay. So here I have the F on this side and these ones on the other side. So there's the friction. F is of course the friction plus this component of the gravity. That's in the correct direction.
Yeah.
That we actually already know. And what we already know is also that the friction is this friction factor times normal force. And then this was the Gx was G sin 5 degrees.
Yeah.
Are you following what I'm doing? Or is this simple or horrible? Simple? Who says simple? Who says horrible?
So, like. I think that.
Okay. Who says okay? There's a lot of paper now being used and a lot of letters that mean something. Then there's the right angle triangle.
Yeah.
And you don't know much about the forces yet either because you didn't go through that theory yet in the physics, yes. But maybe in some school you already did it. Okay.
It's very cool.
Let's calculate this until the end, yes. So the F, I know the F. And I know the N as well. My friend N, I have solved. The N, the supporting force. I know it here. It's this. So now I can put everything into this equation. I'll take it down here. I wanted to calculate the force of the engine that I need to go up this hill inclined in 5-degree angle. So I have there my friction factor. Then I have the N, which appears to be in this kind of calculation. The G times cosine of the angle of the inclination. And then also the I have to also compute this component of the gravity. And then I can still write it once more. So there's the friction factor, then there's the G that was M times G. Then there's the cosine. And then there's the G that was M times G and the sin. And that would be finally my force. The force that I wanted to calculate. To go uphill. Now I would be able to calculate it because I know all the things needed. I know the friction factor for some reason. For sure, when you're trying to go uphill in your village, when it's icy.
Yeah.
Maybe with the icy road, you can evaluate the friction factor. For example, or a normal road. Here it was 0.1. And then I know the mass, that was 1,000 kilos. I know the little g friend here, that was 9.81. I know the angle. So I can just put everything there.
Yeah.
Into this long equation. Yes. So this was 0.1. Then I had the 1,000. I could also take a common factor. But I don't do that. I just put everything there. Okay. And then there's the cosine 5. And then I still have to times sin 5. Now I can put this all into my calculator. Maybe we don't do this kind of a calculation in the exam. No? Yeah?
I think that's all okay.
It's a bonus. No? Yeah, this is not this is just one kind of side path where you can use this. Right angle triangle. Then I need the cosine times the cosine 5. Plus 1,000 times 81 times 5. And I should get some kind of reasonable number. If I don't, my calculator is fixed in radians. Yes. Then I get something weird. So I got the something like this. And this was the newtons. Force was with the newtons. And now I can, of course, round it in the accuracy of two numbers. So it would be about 1,800 newtons. So then if I compare it with driving on a horizontally, it's about the half. Yes.
Yeah.
now when I went up like even on a 5-degree angle, then I already get like, the engine force needs to be double.
Yeah.
How about calculation 9? Do you want to do that? There would be also the acceleration.
Then you would just. Add in. You know where you've got 0, you could just add it, like it's basically the same though, but you add 0.0. You know, there's calculations.
Yeah, but and also you are going downhill. That's actually good consideration.
Yeah,
So which things change there in the calculation 9? How is it different compared to this?
just went down. You would times it by a negative.
Yeah, so this term here.
Yeah.
Is plus. It helps you, yes?
Yeah.
You need less the engine power.
Yeah.
And then also you're accelerating now.
Yeah.
So you need this term there as well. It's not 0.
Yeah.
Otherwise, it's the same.
Yeah.
So it's not that bad.
Yeah.
What if you figure it out at home and we continue with it on next week, and then we finish this topic and go to the next bit? Yes?
Yeah, like. That's in this technical formulas. So, do you know sort of this thing about percentages? You know, just because part of one of the tabs for demand